Recall. In 16.1, we started with rectangles, okay, where we have interval from A to B crossing interval from C to D. So the cross here, once again, is only a notation. It just says, okay, x value is cut between A and B, y value is cut between C and D. So the double integral of this kind of rectangle of f of x, y, dA. So we define this by a limit of a double summation, okay? So basically, you subdivide the interval from A to B into, let's say, m pieces. You subdivide the interval from C to D into, let's say, m pieces, okay? And then for each subdivision, it's a tiny little rectangle. But then you choose some xij, yij as representative. Right? So you calculate the functional value as the height, and then you multiply by the area of the subdivision. Okay? So this is the way that we can Riemann sum. And then we push n and m into infinity. So as long as your function f is continuous, then your limit exists, right? So we just need to specify that delta A, the way that you subdivide, represents the area of the subdivision, which is delta x times delta y. Okay, is the area of the divided subrectangles in the rectangle arc. Okay. So now, if we want to do the extension, we add only one more dimension. So it's going to be really similar. Okay. So now instead of R, let's call it cap B. Okay. It's going to be a rectangular box. That cap B be a rectangular box. So here, cap B is defined by AB, the interval AB crossing the interval CD, crossing another interval from R to S. So basically, this is the set of all points in the three-dimensional space. X, Y, Z are tuples, such that now here my x variable is cut between A and B within the first interval here. Y is cut between C and D, and finally Z is between R and S. Okay, so here we quickly extend the above definition for the double integrals. Okay, so for a triple integral, the notation is that we have three integral symbols. We put cap B at the bottom. So we're gonna accumulate f of x, y, z, the functional value, multiplying by the way that you subdivide this rectangular box B. Okay, so dV is now the way that you subdivide. Now is the volume. Okay, it's a 3D of it. So let's quickly write down the definition. So it's going to be once again Riemann sum kind of a limit. Okay, so it's really similar to what we have done before. So it's going to be a triple integral. So it's the triple summation. So I goes from 1 to, let's say, L. So we divide the interval from A to B to L pieces, from C to D to M pieces. We have ij, and so now we have k. So we have a third index of mm, and then in each subdivision we have a sample point. It's going to be x ijk, y ijk, z ijk. So this is really analog we put a star here to indicate that this is a sample point, and then we do delta V. So LMN goes to infinity. That's the way that you take the limits. Okay. But here, let me quickly write down that delta V here is exactly the volume of the rectangle. So this is delta X, delta Y, delta Z multiply. So that's representing the volume of this subdivision. Here, we firstly define the triple integral over a box. Okay. Basically, we have fixed intervals in terms of x, y, z, right? And then we utilize the Riemann sums to define the way that we calculate the triple integral. Okay. So basically, it's the triple integral over a region B, which is accumulating the function value f of x, y, z, multiplying by the way that you subdivide that region, that solid B. Okay. So, well, instead of a region cap D or cap R, now we here have a solid B in three-dimensional space. So, and the way that we do in the Riemann sum is that for any subdivision, we choose a sample function value. Okay. So, and in the tiny little increment of the volume, this is actually a star box, a star rectangle. So basically, there will be a tiny little width, tiny little height, and tiny little length. Okay. So that's dx, dy, delta x, delta y, delta z. All right. So that's just a straightforward extension. So we also recall that if we are defining the double integral on a rectangle, then we are free to interchange the order of integration whatever way we want, because that's what the Fubini theorem is saying. So that's also true for the three-dimensional case. Okay. Theorem. Fubini. So basically, if f is continuous on the three-dimensional box having intervals from A to B equal x, from C to D equal y, from R to S for z, then we can write the triple integral of f of x, y, z dv. So this can, well, here you can use whatever order that you want. So let's say here, let's put x on the most outside, y in the middle, and z in the inner. Okay, so that's going to be from A to B dx. Then we just follow the order. Okay, so basically we whatever integral sign we put that corresponding differential notation. So here from C to D, that's in the middle, that's for D, that's for y, and from R to S, that's for z. Okay, and finally we put in the function. All right. And actually, the order can be whatever way that we want, as long as you have the this same correspondence. So basically, you can see that when you're doing the integration, the order is going to be from the inner to the outer, right? And order of integration can be changed. As long as you do it right, then there'll be six different orders, right? So basically, here you see this is dz, dy, dx, right? If you have z at the front, you can interchange x and y. It's going to be dz, dx, dy, And then those are 2, right? And then if you let dx to lead, there will be another 2. If you let dy to lead, there will be another 2. So there will be 6 possibilities in total. For example, if you write dy dx dz, if you write dy dz dx, they just write out the integrations accordingly. Because here dx is on the outside, so that tells you we have from A to B for the most outer, and then z is the middle, so z goes from R to S. Finally, for y is from C to D. And you put f of x, y, z there. So here, if you compare, then this is simply interchanging y, z, and then you just interchange the integrals in terms of y, z accordingly from the previous triple integral, iterated triple integral. All right. So that's actually conceptually an extension. So now let's quickly look at an example. So basically, if you have polynomial functions, it's going to be also really simple, like you have seen from double integrals over rectangles. Okay, so if b is the interval from 0 to 1, crossing the interval from -1 to 2, crossing the interval from 0 to 3. So basically, it just says the ranges of x, y, z accordingly. Okay? If you want to calculate the triple integral over this solid with the box B for some polynomial function as x, y, z squared dv. Okay? So here, this is the polynomial, so of course it's continuous. By the Fubini theorem I right above, we know that whatever way that we write down the order is going to be fine. So let's just write dx dy dz, okay, so that we just integrate in terms of x, y, z in a systematic way. So if we do that, then we put z on the almost outer. Okay, so z is from 0 to 3. Let's put that down. And then y is in the middle, it's starting from -1 to 2. X will be from 0 to 1. And then x, y, z squared. And if you have too much space and you're using iPad, you can just move this a little bit forward. All right, so we write dx dy dz, and then we're just gonna integrate from the inner to the outer. Okay, so that's similar to what you have seen from the bivariate. Okay, so now to do the integral in terms of x, we treat y and z as constants. So that's actually pretty straightforward. We have x to the 1 as the function, yz squared is a constant, right? So power function, add 1 divide. So that's going to be 1/2 x squared, yz squared. Okay, so the antiderivative in terms of x is this. And then we plug in x equals 0 and x equals 1. And then we see that x equals 0 doesn't really give you any, doesn't give you anything. Okay, so the evaluation for x equals 1 matters. Okay? And then you copy what you have for dy and z. So this is pretty standard, right? And then we evaluate. So we still copy the most outer 2 layers. Here evaluate. So we just have 1/2 yz squared. And then when we plug in x equals 0, it doesn't give you anything. Okay, dy dz. So it's good. So this is the most inner layer, right? And now, if it's good, then okay, this is just a double integral, double iterated integral. Okay, so that's just something that we have seen already. So you just once again start from the inner. So we have 1/2 z squared as constants. Y is still the whole function with degree 1. So add 1 divide, so it's going to be 1/4 y squared z squared. That's the antiderivative in terms of y. Y goes from -1 to 2. And then integrate in terms of that we need to keep. Okay. Okay, I know this probably was something funny, but not really from what we just did. Okay, so plug in y equal to 2 and y to -1. So 1/4 y 1/4 2 squared, that's just z squared, right? So if you plug in y equals to -1, that's here we minus 1/4. So this y squared is just 1, z squared. So here we have y non-zeros. Okay. So that would be two different functions that we are subtracting. And then finally we integrate from 0 to 3. Easy. So this is actually what? This is actually 3/4 z squared. And then antiderivative, this is add 1 divide, so this is going to be 1/4 z cubed. And finally we evaluate at equals to 0 and so this eventually gives you 1/4 times 27. So that's just so you can see if you have just a triple integral over a box, it's and if you have a polynomial function that you're integrating, it's same old. Okay. So quick remark. Possibly you have been thinking, okay, we have a function as a polynomial. It's actually a monomial. It's only one term, right? So you can separate x, y, z as distinct functions in terms of x, y, z respectively. So based on what you have seen, the double integrals, you can split the double integral into individual double integrals multiplied, right? So that's also doable in the example right above. Okay. So since function f of x, y, z that we just have seen is x, y, z squared. Okay. So x times y times z squared. So here the first part only relates to x. And the middle is a function of y only, right? Only related to y. And finally, that z squared is multiplied on top of xy, right? So this is only about only related to z, right? So here we can just utilize that same result from double integrals over boxes. So here, why not we copy the integral from top that we can do. Here we just need to realize that we can split this into pieces. So we just write the integral in terms of x. in terms of x, and then multiplying by the integral into the y, multiplying by the left integral into the z. And we just write out the bounds of each variable accordingly, right? So for x, by looking at the integral from above, this is from 0 to 1, x dx. And then for y, it's in the middle, so from -1 to 2, y dy. And finally, z is on the most outer, so z is from 0 to 3, z squared dz. Okay. And then, of course, now we split it into 3 different family intervals. So that's actually going to be simple. So x, the antiderivative is 1/2 x squared. Evaluate at x equals 0, x equals 1, and you can see only x equals 1 matters. So y gives you 1/2 x squared, it should be 1/2 y squared, plug in y equals 1, y equals 2. Finally, z squared gives you 1/3 z cubed, that's the entire derivative, evaluate that z equals to 0. Okay. So, and you can expect the answer will be the same as the step from above. Okay, so it's essentially it's going to give you value. Okay. So you can see, okay, from the first evaluation it should be 1/2, right? From the second evaluation it should be 1/2 times 3, right? From the third evaluation it's going to be 9. Okay. So here it's the same thing. If you can split the function in terms of individual functions multiplied, okay, then you can just split the triple integral as well. So you can see quickly we have extended what we are seeing from the first section of this chapter, right? So for double integrals on boxes, then it's going to be relatively straightforward now. Any questions so far? And then the next topic is definitely the well, if you think about it from double integrals, it's double integrals over more general regions, right? So instead of rectangles, we can define it certain closed and bounded regions that can be described. Okay, we have 2 types, right? Type 1 and type 2. So here we want to extend it to more general regions for triple integrals. Extension to general, you can say solid, right? So above we have triple integrals over boxes, but now we have general solids. Okay. How to compute the triple integral over a certain region E for a function f of x, y, z accumulated over the subdivided volumes. Right? So, like we mentioned, we can recall from 16.2. When we talk about type 1 region, basically we start by letting x to be free in an interval, but y is cut between 2 functions in terms of x. Okay. So the type 1 region is where we have all the xy pairs in the xy plane, such that x is cut between interval from a to b. But now instead of y between c and d, we have y between functions in terms of x, g1 and g2. Okay. In terms of x. And you can think of if you can recall that type 2 region is really similar. Then you just have y cut between 2 constants, and x is defined between 2 function in terms of y, right? So in the three-dimensional case, it's a little bit different. So basically, we will have what? We will have a z. So that will be cut between two surfaces, okay? And then so basically, if you think about the solids we have seen, so basically z is cut between two functions in terms of x and y. And these are surfaces. But then these two functions will also be defined on a certain region. So let's quickly illustrate. So it could be something like, let me first establish the axes. So x, y, z, origin. So suppose here we have a solid that has a surrounding surface to be somehow cylindrical. On the top, I have some region like which is surface. The surrounding ones are kind of cylindrical. So let me draw a vertical line going down, and then the surrounding surface is cylindrical. So essentially, here you can imagine these are parallel vertical directions. Okay, so that's what we are not including in the figure. But then we make it transparent. So this is the solid that we have. I probably want to make it a little bit larger. So basically, what do you see here? So basically, here I just mentioned that the surrounding surface is actually cylindrical in the sense that they all follow this vertical direction. Okay, so that's for the surrounding ones, for the surrounding surface. Okay, but then on the top we have a surface in terms of x and y, right? So let's call it, this is the upper bounding, this is like the cap, right? So that's U2 in terms of x and y, okay? And at the bottom, this one is the lower bounding, which we name it as U1. Okay, so U1 is lower bound, U2 is the upper bound for the variable z. Okay, now, okay, so that's the top, that's the ceiling and the bottom. Okay, but then we still want to define everything in terms of x and y. So here is what we do. So since I mentioned that the surrounding surface is actually cylindrical, right? So you can somehow imagine that you extend the directions, you will essentially hit the xy plane, and it will define you a region. So that is possibly something like this. Okay. So this is our region D. So this is our region in terms of the xy plane. Okay, that's all. That's called D. Okay. Let me enclose it in red. All right. So now from the picture, we see that okay, this is the solid E, but then as long as we know, so by verbal description, you can say, okay, this is the solid that's right above the region D in terms of within the xy plane, right above, and then it's upper bounded by our surface U2 and lower bounded by our surface U1, right? So by this description, you can say, okay, as long as I know how to describe the region D in terms of x and y, and then I can just append the I can just append the description of the solid by introducing z, okay, cut between u1 and u2. Okay, so let's put them down. So assume that for the region D, it's in the two-dimensional space, it's the xy plane, right? So you can definitely write something. So let's say we can give a description, let's say type 1. So x is cut between some interval from a to b, and then y is cut between functions. In terms of x, so I can just call them g1 and g2 of x. Okay, so assume we have the description for the region D, right? And then we can just write the triple integral on the solid E of our function f of x, y, z, dv to just follow the way that we described. So we define D, right? We define in terms of x and y for the region D. Finally, we're adding the bound for z to be cut between these surfaces u1 and u2. So we just do that. So for x is from a to b, dx, we keep it there. For y, so we have g1 of x as the lower bound, g2 of x as the upper bound, dy. So far, that's just describing in terms of the region D, right? But now we introduce the bounds for z. So the z, so now z goes just from u1 of xy to u2 of xy. Okay. And finally, since we're integrating the function f of x, y, z, then we make a little bit more space and we put that function back in. Right. So here, what we have done is that we just appended the bounds for z right after the description for the red set cap D, right? So we mark. So here we wrote the triple integral, right? But then if you want to write down the set notation for this solid E, then these this is defined by all the tuples such that my xy pair is cut within the region D in red, right? And then we follow by the bounds for the last variable z. Okay, so z is cut between u1 of xy and u2 of xy. And further, we assumed in red that D is now a type 1 region. So if you assume that, then you can just write it alternatively by explicitly write out all the bounds. So here x is cut between a and b. Just copy what you have in the red set D. Okay, so g1 x is upper bounded by 1 and is further upper bounded by g2 of x. And finally, we append the bounds for z. So now you can see that the later variables rely on the prior, right? So here we see that y is relying on x, but now z relies on both x and y. Okay, so u1 of xy and u2 of xy. Okay, so you can see this is indeed a long description as a set, but then this is exactly following the description for the triple integral right above. Okay. So basically, if you can write down the triple integral, you can definitely write down the description of the solid and vice versa. It's the same thing. So far, so good. Right. So now the next remark. So here we started with what? We started with this figure. So here in this figure, what we have done. So let's zoom out a little bit. So in this figure, what we have done is that okay, we have a solid. Well, for the illustration, we mentioned that the surrounding vertical surface is actually cylindrical, right? So basically, it tells you that that's actually vertical, and all if you project it all the way down to the xy plane, then it will form you that region, right? But then, so this is essentially just doing a projection down to a plane, right? And then xy plane is not really special, so you can still do the projection of the solid right here onto the plane on the back, which is the YZ plane. Okay? So if you do a projection there, then essentially you will have a region. We still call it D. So it will give you a region in the YZ plane, and then there will be upper bounding and lower bounding surfaces also, but it's in terms of YZ, right? And also you can do that projection onto the plane on the left, which is the XZ plane. Okay? So if you do the projection along that direction, that will be a different description. Okay, so there are certain different descriptions, and that's really up to what plane that you're projecting it on. Okay. So here we mark. We may also have two more types of description for the solid. Okay. So we can write it as so here let me cheat by copying this part. So the only thing different is that here we project onto let's say the YZ plane, and everything is in the YZ. Okay. So if you project down to the YZ plane, then this certain region, let's call it D again. But then your X variable is now cut between two surfaces right above the region B. Okay. Or if you project it down to the XZ plane, it's going to be the same idea. So it will give you a region, and the last variable will be relying on that region. So XZ. Okay. So in the XZ plane, there could be another region. Now we name this D again. Then the Y variable is now cut between two functions, two surfaces in terms of XZ. So of course, here we see, okay, we have three types, and each type for these regions, we do have order, right? So if you have X to be first, then the region D on the top will have two kinds of descriptions, and the D in the middle, depending on whether you have Y leading or Z leading, there will be two different descriptions, and finally for the last one, if you have Z leading or X leading, there will be also two different descriptions. So indeed, there's going to be a total of 6 possible ways that you can describe a solid. Let's look at an example. So let's say we are looking at the triple integral over the solid E of f of x, y, z dB, where so now the solid matters. Okay, so E is the region bounded by paraboloid y equals to x squared plus z squared, and the plane. y equals to 4. So if you're looking at this paraboloid, this is saying what? This is saying, okay, if I fix x to be a constant, I will get y equals to z squared plus a constant, right? If you have z as a constant, you will have y equals to x squared plus constant. Okay, so these are both parabolas opening along the y-axis. Okay. And then here, if you fix z, if you fix y as a constant, you will get circles. Okay. So along the y direction, they're saying we're actually going towards the right. Okay, so you have a you have a paraboloid. And then we here on the right hand, we have y equal to 4 as the plane. Okay. Y-axis. So these are x and z axes on the region. That's our solid. Okay. So the surface here is y equals to x squared plus b squared. And this is the plane. That's the upper bound, right? So basically, the paraboloid is the lower bound, and then the upper bound is here, is the plane, the vertical plane, y equal. And by the way, we mentioned that okay, whatever y value that you fix actually is doing what? Actually is doing there's a vertical plane which says y is a constant, right? And then in this plane, you will have that's actually doing an intersection, right? So that's like a trace. So you fix y to be a constant, that will get you a circle. It tells you what? It tells you the origin in terms of the x and z plane, right? So this is a plane in terms of the z, and then that y-axis is actually the center of the symmetry, right? So it tells you what? It tells you y. The y-axis is actually the axis of symmetry. So this is axis of symmetry. Just by looking at the figure. Okay. So basically, okay. So upon these observations, what we can say more is that right above we have 3 ways to do projections, right? But then you can see that this solid actually contains the y-axis, which is the axis of symmetry. So basically, if you think about projecting it on the xy plane, it will so this plane will cut through this paraboloid, right? And then if you think about the projection onto the YZ plane, it's also similar, okay? Because that projection, this YZ plane also contains that axis of symmetry. Okay? So basically, it will just cut through the middle. Either way, it's going to be similar. Okay? And finally, the one that's not similar will be the one that's projecting onto the plane on the left. Okay? So this is just quickly mention this. But if you do the projection onto the XZ plane, then you will get a circle, right? So you get a disk. So the largest disk is right here at the top. Okay? So for this one, you can just cylindrically move it to the XZ plane. That will give you the largest possible shadow. Okay? So that the largest possible circle there. Okay? So we're gonna do. So here we're gonna do the projection onto the XY plane, and then the projection onto the XZ plane. Okay, to represent this solid. To represent the solid E. So here decide the region D first. So basically, this is just saying, okay, we are projecting onto what plane? Okay. So like we mentioned, X, Y, and X, Y, and YZ, they are really similar. So we project on the XY plane. So And as we mentioned, the XY plane cuts through this solid, right? So we quickly establish that axis again. Okay, so basically we are looking at the cross section. So what does it look like? So essentially, let's quickly sketch. So here there's going to be a straight line, but then there will be the intersection is going to be a parabola, right? It's going to be a parabola that's going well, which is the intersection of the surface y equal to x squared plus z squared with the horizontal plane. Okay, next one. So that tells you what? It tells you within that plane z equals to 0. Okay, so you just plug in z equal to 0 into the surface. That will give you a parabola. And we just quickly sketch it like this. Okay. So this is the parabola, which is the intersection of y equal to x squared plus z squared and z equals 0. Okay. And it tells you this thing is 0. Z squared is 0. So that tells you, okay, basically we just have y equal to x squared, right? And for the intersection with of the plane y equal to 4 with this horizontal plane, that will give you this this part, the straight line, the line segment, which is y equal to 4 intersecting with z equal to 0. So you see, okay, basically x is free, but then you need to know what's the bound. Okay? So that's good about the projection part. So this is well, in this sense, the projection is indeed an intersection. Okay. Okay. So any questions? So that's the region D, right? So we have surrounding region D. I'm going to put the letter D to indicate. Okay, that's the region D. All right. So now, as long as we decide D, then we need two more things. Okay, we need U1 and U2. If you recall, basically we need the lower bound over this region for the solid, and we need the upper bound, right? So basically, let's cut it again. So here we cut it in the middle. So the surface will be cut into two pieces, right? And actually that's separated by the parabola that we just established. Okay, so there's a top, there's a bottom. So to illustrate that, basically from the parabola, there's a top. So this is the top half of the paraboloid. So that's called z equals to u2 of xy. And then for the same parabola, there's a bottom part. Well, yeah. So this is the bottom half of the surface of the paraboloid, which we call as z equals to u1 of xy. Right. Now a close look. So the idea is not so complicated, but still we need two things. We need the explicit description of the region D, and we need the descriptions for U1 and U2. Okay, so we will do we will get them by solving certain things. Okay, so in particular for the region D, it's actually what? It's actually a region in terms of the XY plane that's enclosed by a parabola and a line, right? So we just draw it in the regular way. So we see here the horizontal axis is x, the vertical axis is y, and then you just have a parabola. And you have a line. So the parabola is y equal to x squared, as we identified from the top, right? And the line is y equal to 4. Okay, so the region D is the region enclosed by the parabola and the line, right? So this tells you this is the y-intercept 4. We have the origin as the bottom point. Okay, so it's not really hard to identify the intersection. So this should be negative 2, 4. This should be 2, 4, right? And then of course there are 2 ways to describe the region D. So you can say if you use vertical bars, then x is cut between negative 2 to 2. Let's quickly write it down. So here D equals to all the xy pairs such that I can say x is cut between negative 2 to 2. And y is cut between, okay, so the lower bound is actually the parabola. The upper bound is the line. So y is lower bounded by x squared, upper bounded by 4. And of course, now if you think about the horizontal bars, then okay, so y is between, so yeah, let's quickly write it down. So just as a side note, okay, so xy pairs such that I have y should be between 0 and 4. But now here you need to notice that you are trying to get the x coordinates for a fixed y value on the parabola, right? So this is saying, okay, my x value is plus or minus square root of 1, right? So solving the parabola equation to get the solution for the x coordinates. So the x is cut between negative square root of 1 and positive square root of 1. So either way, it's going to give you the description for the region D. So is it? Right. So now let's look at the 2 surfaces. So we have the top half and bottom half, right? So we just need to describe U1 and U2. Okay. So for the top half, so we are talking about the top half, bottom half, right? But it's the top half and bottom half of the paraboloid y equals to x squared plus z squared. Okay. So here, what do we need? We need the z value, right? So basically, this is just saying, okay, I need to describe everything in terms of z. Excuse me. The variables are x and y. We want to solve for z. Okay, we want the explicit description for z. Okay. So here, this is again a quadratic equation in terms of z, right? And then we want to solve it. So here, in another way, this is written as z squared equals to y minus x squared. Okay. And then there will be 2 solutions. So the positive one will be the upper bound. So on the top half, since z is non-negative, we have z equals to the positive square root of the right-hand side. And the bottom half, that's beneath the xy plane. Okay, so the z is non-positive. We have z to be the negative of the square root. Okay. So we have U2 and U1 respectively. Okay. So now we do have everything we can put together and we can put the things down. Here, hence, we have E to be all the x, y, z tuples. So here I'm gonna use what we described in black. Okay, so we just use x cut between negative 2 to 2, we followed by y half between function in terms of x, and finally, we have z half between two surfaces, okay, y minus x squared under the radical and lower bounded by this negative of that. And let me quickly write down the triple integral in the iterated form, okay? So the triple integral over the solid E, in this description, we just directly copy down the bounds in the same order, okay? So basically, this is negative 2 to 2 dx, x squared to 4 dy, and finally, negative the radical to the positive radical dv, and yeah, I probably need a little more space for the function f of x. So the last method is that we project onto the plane on the left, okay, the x-axis. Okay. So and now basically, when you think about the x-axis plane, that's actually the plane where y equals 0, okay, right here. And then, so basically, if you're thinking about those planes that have constant y, then this one on the right hand, okay, this ceiling actually is the largest circle, right? This is the largest cross section between those vertical planes and your paraboloid. Okay, so for those ones that have lesser y values, then you have smaller circles. Right. So it tells you what? It tells you basically the circle on the right end, that's actually gonna be the shadow that you project onto the x-axis. That forms the projection onto the x-axis. And here, basically, you see, okay, that so the shape of these is definitely the same as the shape of this cross section right here, right? So that's actually what? That's actually y equals to x squared plus z squared, and at the same time y must equal to 4, right? So the boundary of this cross section and black circle, this is actually the intersection of your paraboloid and the plane on the right. Okay, so and it also happens to be that lower bounding and upper bounding functions in terms of x and z. Okay, so here we can see that the lower bound is exactly the paraboloid itself. So y equals to, we name it u1 because this is the lower bound. And of course, the upper bound is just the plane y equals to 4. Okay, and we call it u2. Okay, and the intersection is of course just the circle that here you have to have the intersection, so but both equations must be satisfied, that it tells you x squared plus z squared must be 4. Okay. So B is the projection of solid E onto the x plane. And if we write it out, that's xc, such that basically the boundary is x squared plus z squared equals 4, right? So the disk itself will be x squared plus z squared less than equal to 4. So it will enclose everything within the boundary. Right. So now we do have the region D, and we have the upper and the lower surfaces that's bounding the solid. Okay. And of course, we know how to describe the disk, right? But let's just quickly close a look. So we have a circle in the x-y plane. Okay. So basically, the circle is centered at the origin, and the radius is 2, right? So x squared plus 6 squared is 2 squared. 2, 2. And then here we have, again, multiple ways to describe it. So this is really up to which variable you are solving. So basically here, if you say, okay, I'm going to cover this region by using vertical bars, okay, then you're trying to fix the x values from -2 to 2, and then you're looking for the z coordinates on these upper and lower semicircles, right? So it tells you what z must equal to plus or minus the radical of 4 minus x squared. Right? And if you do the other way, if you do the horizontal coverage, using horizontal bars to cover, then you are solving for x values. Right? So here we can quickly do. So d equals, so this is something from the previous sections. So here we have all the xc pairs. And now, so let's say if we do it in red using the vertical bars, then x is free from -2 to 2. And then my z value cut between the upper and lower solid right? So here z must be, the upper bound is square root of 4 minus x squared. The lower bound is the negative solution. Right. So here then now we have the description of the clearly, and then we have the U1 and U2 as the bounds for the last coordinate. Hence, we can write down the solid V to be all the x, y, z tuples such that. So basically, we just use that red description that we have on the right. So basically, we start with x, so -2 to 2. And then z, we are using function of x to bound. And finally, we have what? We have y is cut between u1 and u2. Okay. And you see u1 and u2 are functions in terms of x and z at the same time. Right. So, and then if we want to write down the triple integral in an alternative way, we just follow this description of V. Okay. So the triple integral of the solid of the function multiplying by dv, the way that you subdivide solid. So basically we have, so here we just follow the order. So this is negative 2 to 2 dx. And then on the inner we have z goes from the negative radical to the positive one. And then we do dz. Finally, we have y cut between sum of squares and 4 dy. So that's about the triple integral and the dv, right? And then we put in the function. And so up to this point, we have done two kinds of projections. Y integrate z before y. So here we have this. And so well, this question I'm thinking is not entirely clear, but basically we write down the integral in terms of z first, then y, because we're describing the solid in this order right here. So we start with x. Basically, for the region D at the bottom, well on the left hand, which is this, right? So we have x to be free between -2 and 2, and then we're using vertical bars to cover. So x first, then z, right? And finally, we have the solid that's well, in terms of y now, it's lower bounded by the parabola right here, and upper bounded by the plane right here. So now, once we describe E in this way, then we just write down the integral accordingly, right? So this is actually a very good question, since indeed we have decided. So for this region D that we just covered right here in this figure, we decided to use the vertical bars, okay? And then if you're using the horizontal bars in purple, then it's going to be z from -2 to 2. And then x with the bounds cut between those purple points. Okay? And finally, y is using the same lower upper bounds. Okay? So you see, once you decide the region D, then there will be two ways to describe the solid. Right? And of course, earlier in the previous solution, we have the projection onto the xy plane, right? So that's there will be two descriptions as well. So, but then if you want to explicitly write down everything, then you can probably do that yourself. Okay. So once again, like right here, right? So basically, we describe this region D, which is enclosed by the parabola and the line. So this is the purple. This is vertical bars. Okay, and in red, I have the description for D in terms of the horizontal bars. But of course, we only use the vertical bar description to describe E, and of course, you can use that to write down E from here. Okay, so first Y, then X, then Z. Right. So that's something you can do also. So these are two. So these are actually two ways. Okay. The alternative solution at the end we just did. That's also two ways. And like I said earlier, if you are doing a cross section where you have well, excuse me, when we are doing the projection onto the YZ plane, there will be another two different descriptions. Okay, so this kind of questions is very important. So we will see more examples. But basically, indeed, there are different ways that you can describe a solid, and then you will be able to write down the triple integral in alternative ways. Okay? So quick remark. So the steps for setting up triple integrals. So the first step, identify the region D. Okay. Definition of D can be used to set up the most outer and middle integrals. Then once we decide D, we have the second step that we need to identify the surfaces U1 and U2. For the most inner integrals. And of course, once we have everything, then we put the things together. Okay. So basically, when you try to identify the D, the region D, let's say, okay, you must decide that plane that you're projecting the solid onto, right? So that tells you you have to decide two variables, and then the last variable will be cut between U1 and U2, which are functions in the original first two variables. Okay. So the key components are, of course, the region D and the two bounds surfaces. So another remark. So here we have the triple integrals that are integrated in the function of this little f, right? And in the special case that little f is a constant, 1, then you are essentially accumulating dv, right? Just triple integral over the solid D of dv. So that's actually just accumulating the entire volume of the solid. So actually this one relates to one of the previous remarks in the section of double integrals. Recall that in 16.2 you have the double integral of the region D of f of xy minus g of xy dA. So this is the situation where, okay, you're over the region D, and then you have an upper bounding function f, lower bounding function g. These are two surfaces, right? So basically, this is the volume that's describing the solid that's above the region D and cut between the two surfaces f and g. Okay. So now we can rewrite it in another way. Okay. So this is actually, okay, we still keep the double integral dA there, but then the difference f minus g here, it can be written as what as the integral in terms of dz that we have the lower limit of the integral to be g and the upper limit of the integral to be f. Okay, so we can write the inner difference as a single interval right here. And finally, so basically that this blank here, you can just replace it by 1, or that function little f as a constant. So recall that this double integral provides the volume for this. So volume ends with the E, I think. So volume of solid between the surfaces Z equals f of x, y, and Z equal to G of x, y over region D. Assuming f of x, y is lower bounded by G of x, y over the entire region. For all x, y pair within the region. So now you see the red intervals. This is exactly one way that you write down the triple integral over the solid. Okay, so these are how things related. But of course, here in triple integrals, in general, if you have a non-constant f, then indeed you are extending what you have seen in the double integrals. Okay? Another example. So we look at one more solid. Okay, so we have the triple. So this is written in the iterated interval form. So from 0 to 1. So let me just write down the bounds. So the inner is from square root x to 1, and then the most inner is from 0 to 1 minus y. We integrate f of x to y, z, and dz dy dx. Okay, so this tells you what? It tells you, okay, so by looking at the most outer layer, let's say my x is cut between 0 and 1, and now y relies on x, and y lies between square root x and 1, and finally z is cut between 0 and 1 minus 1. Okay. So here the question is, can we change the order of integration to dx dy dt? Okay, so here we are given an iterated triple integral in the order of dz dy dx. Okay, and here we want to interchange the order into dx dy dz. So basically, what's the difference? The difference here is that for dz dx dy dx, this is actually saying we are projecting onto the xy plane. Okay, and further, x is free and y relies on x. Okay, so that tells you the way that you're covering that region. But then for dx dy dz that we want here, we are projecting onto the yz plane. Okay. And then also z is free and y relies on z. Finally, x relies on both y and z for the way that we're looking at. Okay. So let's try to recover that solid from the iterated interval. Okay. Here. So the solid is actually described by the bounds of this interval. So the solid E is the following. So we have all the tuples, x, y, z. Here, like we mentioned, x is free between 0 and 1. We just follow the order of the iterative interval. So y is cut between square root x and 1. And finally, z is cut between 0 and 1. Okay. So basically, this description right here, there's always a good way that you can use some computational tool to get the geometry by doing some plotting. Okay. So here, there are online websites and or softwares that you are able to utilize to plot the solid. Okay. But here, in class, we're just gonna do the sketching. Okay. So, like we mentioned, this solid D is now relying on x and y, right? So basically, we can do the illustration by sketching. So this is the xy plane. And then here, what we see is that x is cut between 0 and 1. So it's right here. And then we see, okay, now y is cut between 1 and square root of x. Okay, so y is cut between two functions. So for the left hand side, we have y equal to square root of x as a lower bounding function. The upper bounding function is y equals 1. Right, so y equals 1 is the horizontal line that we can draw really quickly. Okay. And here we have x equals 1 right here. So this is y equals 1. And now y equals square root of x, right? That's actually the square root function. In another way, you can say x equals to y squared. Okay, so this is a parabola opening on the right hand side. Opening towards the right. Let me make it a little more curvy.
It's saying that the meeting's about to be ended.
Oh, so yeah, I didn't notice when I'm not looking on the iPad, but okay, so it shouldn't be ending. Right, so where were we? So here, y equals 1, that's the upper bounding function, that's the horizontal line. The lower bounding function is y equals to square root of x. Okay, so that's the parabola opening on the towards the right. And this is the intersection. And of course, the intersection is 1, 1. Right? And we know that the region is actually this region D that's enclosed by the parabola and the horizontal line, and of course the two vertical lines. Okay, so basically, when you say x is between 0 and 1, they say okay, it is cut between the two vertical lines. Okay, x equals 0 and x equals 1. That was good. Right. So this recovers the region D now. And finally, what do we know? We know, okay, so the projection of the solid onto the plane will be this. That means what? That means somehow if you imagine, so this region D right here, the shaded region, you want to somehow, if you want to recover that solid, the solid will be bounded by this line right here, which is a vertical plane that's going out of the monitor. Okay, and this is another vertical plane that's y equals 1. That's also just going out of the plane of the monitor. And finally, we have a parabola, which is a curve. Then you can imagine that you can extend it like a cylindrical shape all the way out. Okay, so the solid will be bounded by these three boundaries. And finally, what do we know? We know from here that uy is actually 0. okay, z equals 0. U2 is z equals to 1 minus y. So these are planes. Okay. So if we establish those yeah, let me quickly sketch the y-plane plane. So basically we have this. So the upper bounding function is z equals to 1 minus y, right? So this tells you what y plus z is 1. So yz, this is z equals to 1 minus y, right? And let me fill out the axes and the origin. So here I'm doing the shading because I want to also include the x-axis, and x-axis is actually pointing towards yourself, right? So basically here, this is the upper bounding plane, z equals to 1 minus y. And the x-axis is pointing out. Right, so now basically if you think about it, this plane is the upper bounding plane, right? And now the lower bounding plane is what? Is z equals 0. Z equals 0 is actually the xy plane, this one. Right. So basically you somehow need to imagine that the solid is caught between these two planes. And now let's also fill out that region D within the figure. So you just need to notice that okay, the xy plane is right here. So these are the xy axis, and then this ray right here. This is the line y equals 1, right? So that's the line right here in the figure right here. So we want to draw that parabola opening along the x direction and intersect that line at a point. Okay, so let's do that like this. All right. And that region D is this region right here. Okay. So this is 1. So if you must identify that intersection, this right, that's 1, 1. So x equals 1 and y equals 1. So that's good. And now, if you're looking at this shape, well, it's not really clear what the front looks like, but the back is on the YZ plane right here. So that's the back end. Okay? And this side, that's actually this is the intersection of two planes, and also that is the boundary of the bottom solid. Okay? And finally, we need to mention that this boundary in dash right here, this is the curvy part, right? But then you can imagine that you can draw draw it vertically up so that it will form the boundary of the solid in the front. Okay, so let's quickly do that in another figure. So x, z, so here, only the y-axis is going to be dashed at first. That's the transparency right here for the segment from 0 to 1. And then on the top, we still have that line. And you see that it even goes along the x-axis for 1 unit, right? But then, okay, so now the dashed curve is going to be the front. And we know the equation. But then we want to get the front by extending it, well, vertically up, right? So like a cylinder, right? So you see, to quickly mention, So basically, we're drawing in red a intersection of that cylindrical shape and the plane at the top. Okay? So that's actually a curve, but we can talk about the details a little later. But then this is the cylindrical shape that's drawing vertically up from that curve. Okay, so the point here is that this boundary, like we mentioned, if you draw that cylindrical shape all the way up perpendicular to the plane in front of you, it will intersect the ceiling, which is a plane right here. Okay, so these two will intersect, and that will give you the cylindrical shape that you see in front of the solid. Okay, and so basically, the equation of the thing is exactly what is exactly y equals square root of x. Okay, right here. Or in another way, you can write it as x equals y squared. And here x is non-negative. And move it to the left a little bit. Here, x is non-negative. So the curve at the bottom is y equals square root of x. And now, of course, the top plane is y plus z equals 1. So this is the solid that we need, that we want. Okay, so x, y, z couples such that, okay, let me quickly just copy these. So this is the this is the illustration of the solid. So now basically there are a few boundaries. Okay, so let me see, 1, 2, 3, 4. Okay, so at the bottom that's the xy plane. At the back that's the yz plane as a triangle, right? And in the front we have on the right hand side that's the ceiling, which is the plane y plus equals 1, and in the front we have that curvy more quadratic shape. Okay, so basically, if you extend it vertically up, that's exactly that quadratic plane, quadratic surface y x equals y squared, okay, or y equals square root of x. So far so good. All right. So now, if this is good, then let's think back about the question. So we want to interchange the order of the integral into dx, dy, dz, right? To change the order to dx, dy, dz, then what do? We need to project this solid onto the yz plane. Okay. Onto. But well, in this figure, I would say a projection onto the yz plane is not really complicated because that's actually the triangle right there, right? So the triangle at the back. So to just get that, so basically we have yz plane at the back. So this is the line which is z equals to 1 minus y. or y equals to 1 minus z, depending on which variable you are solving it for. But basically, it's bounded by the axes and the line. It's bounded by the axes and the line, right? So to shade it, okay. So this is the so this is the region D if we want to project onto the YZ plane. Okay. And then depending on whether you're using the vertical bars or horizontal bars to cover, then that gives you the distribution for the region D. Okay, so let's see. So we were doing vertical bars. Okay, so now let's do a horizontal one. Okay. So if we're doing the horizontal ones, then now your z is free between 0 and 1. Okay, so quickly, so these intercepts are ones. So z is between 0 and 1. Oh, by the way, so here we are doing the so dx dy dz, right? So z is the most outer, so that's the free variable. Okay, so that's the reason that we decide z to be free first. So z is between 0 and 1, so it's definitely horizontal bars. And then y is cut between 0 and 1 minus z. Okay. So we are looking for the y coordinates of the ends of the segments. All right, so that's the region. And then, so now we need to look for the functions in terms of y and z for the ceiling and the bottom, right? So the ceiling is exactly this surface right here, okay, in red. So that's actually what? That's actually x equals to y squared, right? So we want to describe x, okay, as the function in terms of y and z. And the bottom is what? The bottom is the yz plane. That's actually x equals 0. Okay. Thus, by observing along the x-axis and noting the two surfaces x equals 0 and x equals to y squared as the bounds. And here it's clear that y squared is upper bounded, is lower bounded by 0. Okay, so of course, y squared is non-negative. So that's the upper bound. We have. So this is so basically what the upper bounding function is lower bounded by the lower bounding function is clear from the figure, right? But mathematically speaking, whenever you write it out, it should be following this kind of relationship. Otherwise, there's probably something wrong with the calculation rules. But basically now we can write down the variable explicitly, right? So we just follow the order that we have. So basically we have z first. So z from 0 to 1 is z. Y goes from 0 to 1 minus z dy. Finally, we have the bounds for x. Okay, so it's from 0 to y squared dx. And we fill out the function. And with any questions so far? So this is a typical example that okay we start with one out of the 6 orders, and then we want you to identify a particular order that's given. Okay? So and any questions? If there's no questions, here I'm going to ask you one. Okay, so here, I would like to quickly mention that the solid that we established right here in the figure, right? And now the projection onto the YZ plane is actually not so difficult, okay, because the bottom of the solid along the x-axis direction is actually within the YZ plane, right? So if you are doing the projection onto the XY plane, that's actually what we started with, right? What happens if you want to project onto the XZ plane? What do you think? So so basically, let me quickly mention what you need to watch out for the projection on to the YZ plane, excuse me, XZ plane right here, all the way to the left. Okay, so this is definitely something related to the geometry that you need to interpret. Okay, so at first you should know that okay, the projection of the solid onto the XZ plane, they must have the parts on the x-axis and z-axis, right? Because for z-axis, that's this portion right here. Okay? So between well, on the z-axis between 0 and 1, everything is here. Okay? So that line segment must be in the projection. Okay? And then this segment, this is actually parallel to the x-axis. Okay? So if you project to the left-hand side, it also is also included along the x-axis. And finally, we need to know the boundary of the region within the x plane. So let me quickly put down as a comment. So the boundary will relate to this intersection red curve right here. Okay? So let me quickly write that down. So what is the question? Okay. What is the projection of the solid B onto XZ plane? So, like I mentioned, so the line segment along the x-axis between 0 and 1, and the line segment between 0 and 1 along the z-axis, they are going to be included, okay, within the projection. And then there's a certain boundary on the top. This is something that you get when you project this curve onto the onto the XZ plane, right? So this end will go to this point right here. This point stays, right? So that that the curve in red will result in some curve, right? So how do we get that equation? So here we just need to realize that this curve in red is what? Is the intersection of the quadratic surface and the plane on the top. Okay? So the quadratic surface is y equals to square root of x. Okay. So we need to put them down together. And then the plane at the top is y equal to minus. Okay. Eliminate y, we will get. So this tells you what? This tells you z square root of x must equal to 1 minus z, or z equals to 1 minus square root of x. Okay. So this tells you the equation of the boundary right here. Okay. So basically, if you're looking at the description of the region within the XZ plane, you realize that within the plane there's no y variable, right? So this is exactly why we put the equations of the surfaces that you are intersecting together and eliminate the y variable. Okay. So this one is either z equals to 1 minus square root of x, or if you describe it another way, this is x equals to 1 minus the whole thing squared. Okay. So this gives you the way that you describe this projected region D. Right? So the more figures that you play with and the more experience that you get for this kind of 3D imagination, the better. Okay.